Hi everyone, welcome back to the channel. I'm the GCSE science teacher. In today's video, we're going to be revising all the content for paper 2 physics for GCSE students. If you do enjoy this video and you find it helpful, feel free to let me know by giving the video a big thumbs up, share it with someone else so they don't miss out on key revision. And so you don't miss out, please do subscribe and join our amazing community here. And thank you so much. If you already have done that, I really do appreciate your support. So let's get started. So the first thing you want to know in this topic is the forces topic. Now, this is a absolutely massive topic. There's so many things to know. So I really do recommend you spend quite a bit of time revising this, especially in the lead up to your exam. It's worth knowing the key equations, looking at the equation sheet and seeing what you need to remember. There are a few equations that you aren't given, so it's definitely worth knowing those and also practicing the maths for science in this topic. So let's start off with the scalar and vector quantities you should know. Remember, scalar quantities only have magnitude or size, whereas vector quantities have magnitude and direction. So scalar quantities include distance, speed, mass, temperature, pressure, volume, and work. We need to know vector quantities include displacement, velocity, acceleration, force, weight, and momentum. And throughout this topic, you'll be using these different quantities in maths to calculate different quantities, but also you could be asked to plot this in a graphical format as well. And this does link nicely to some of the required practicals throughout the course as well. Now, speaking of forces as a vector quantity, you need to know the two categories of forces, either contact or non-contact. So some of those contact forces include friction, air resistance, tension, and normal contact force. Non-contact forces include gravitational, electrostatic, and magnetic forces. Now, remember, there is a required practical link to forces, specifically Hooke's law. And Hooke's law basically states that the force is directly proportional to the extension of a spring. So the more force you apply to that spring, the more extended it will get. And there is a key graph that you should know where there is a limit of proportionality, and actually this can lead to deformation. If you stretch a spring far too much, it won't basically spring back into shape. Hooke's law is a good practical to revise because it often does have questions related to it. It's worth knowing the method for it, but it's also worth knowing that graph and also any data that could be asked of you in terms of calculating the mean average, using data in a table to plot a graph as well. Also, remember the equation F, which is force, equals KE. K is just the spring constant, and this is a constant for a particular type of spring. Essentially, it's the stiffness of a spring, and each spring has its own spring constant K. Now, in terms of forces and diagrams, you need to know that representing a force is quite straightforward. All you need to do is draw an arrow, and the arrow shows essentially the direction of that force, but it also shows the magnitude as well. So the length of the arrow is also really important. As you can see in this diagram, there are two forces acting on an object, and essentially the overall or net force, which is also known as the resultant force, is 7 newtons, because what we've done is we've taken the difference between the 10 newtons and 3 newtons to get 7. Now, if these forces were the same, if we had 10 newtons on each side but in different directions, we'd actually say the resultant force is 0. And this is what we call a balanced situation. And essentially that means there is no overall force acting on it. This could mean the object is stationary, so it's not moving, or it could mean the object continues to move at a steady speed and is not accelerating or decelerating, which leads me nicely onto Newton's laws of motion. So Newton's first law of motion states that an object will continue to move at a constant speed or remain stationary until another force applied on that object occurs. And essentially that can cause an acceleration, which links to the second law of motion that Newton had. So the second law states that an object will accelerate if an external force is applied. So you need to know the equation F equals ma, where force is F, m is the mass in kilograms, and a is the acceleration in meters per second squared. You should be able to use that equation to calculate any unknown quantity. And then lastly, Newton's third law of motion. For every action, there is an equal and opposite reaction. So I want you to imagine you're sat on a chair. The reason you don't fall through the chair is because although you have the force of gravity or weight acting downwards, you also have an equal and opposite force acting upwards that keeps you on that chair. So you are stationary on that seat. And that's why those forces essentially are balanced that keep you in that correct position. So we can represent forces using something called a free body diagram. And essentially you would just draw a small circular point or a small box instead of the actual image or the object that's moving. And those forces are represented, as I said, as arrows. And the size of those arrows will indicate the magnitude. And therefore we also have the direction if it is an arrow as well. So just be aware of that. Also make sure that those forces, when you're drawing them, you use a ruler, a pencil, and you also make sure you label what those forces are if necessary. You should also be very careful to make sure that those arrows are on the center of mass of that object. So you're not just drawing an arrow next to an object, you're actually attaching it to that particular object to show that it's actually being applied to that one. Another type of thing you should know as a higher tier student is something called resolving forces. Now, this is slightly more complicated and it requires you to do some maths and use different pieces of equipment, such as a compass, to work out angles and things like this. So what you need to do in the exam, they'll give you a question. It will say there's an object like a boat and it has two forces applying to it and it's causing motion in that object. Work out the overall force by resolving those forces that are applied. Now, the reason you're saying resolving forces is because those forces are acting at angles to each other. So they're not at 90 degrees or they're not in a linear state. They're in a diagonal direction based on that angle. So in this case here, we have a boat that's moving and we have two forces acting on it. We have 50 newtons and 80 newtons, and they are separated by an angle of 60 degrees. Now, what you need to do is you need to draw that out. So the free body diagram would look something like the one I've drawn. Instead of the boat, I would just draw a little dot or a square, but I've obviously shown this to make it a bit more visually appealing. The angle itself, you would draw based on the angle given in the question. So I would recommend you draw a nice straight line that's horizontal first of all, and then you draw your angle, and then you would draw your second force. Now, how much do you draw? How long is the arrow? This depends on the scale that you use. So I would go for something sensible, like 1 centimeter equals 10 newtons. It does depend on the size of the force they give you, but usually it's going to be something like 50 or 60 or 80, something like that. Okay, so the more practice of this you get, the better you'll get at it. So once you've drawn out your arrows and you have drawn your angle using that compass and the second force as well, you'll see you get a diagram that looks something like mine. Now, to work out the resultant force, we simply need to draw a parallelogram. And what you do is between those two forces, where they meet at the tip, you will draw a nice straight line through them and draw a nice parallelogram. And you can see I've done that with the dotted line here. Now, how do you know how large that parallelogram goes? Well, again, you're going to make sure that it's nice and parallel to each other. So that top and bottom line should be left and right line should also be parallel to them. You could also measure the angles to make sure that they are the same throughout. Actually, to prove and show that this is a parallelogram, make sure that the angles that are opposite each other are the same, and that way you know you've made a correct, perfect parallelogram. So you can do that with your compass to double check. Now, what you want to do once you've drawn your perfect parallelogram is you want to measure the resultant force through the middle of those forces you were given in the question, like I have done. And this came out for me as 113.5 newtons. Now, this is newtons that I've converted it to. Of course, that's not going to be centimeters, because what you're going to do is you're going to measure that length and you'll get centimeters, but you need to use your scale to convert it back into newtons. So that's why your scale is really important. Now, they do give you a bit of a range of answers here because, of course, there will always be some slight discrepancies between one person's answer and another. But my key advice for you is practice this type of question and, of course, be as neat as possible. Use a pencil, use a ruler, and use that compass too. So another key idea you need to know is speed, distance, and time and how they are related to each other. There are lots of equations that you should know, but also the graphs that go with this topic. So one of the equations is S equals VT, or distance equals velocity times time. Remember, if you want to put this into just like a speed equation, you could just write speed is equal to distance divided by time. So S actually represents displacement. Don't get confused thinking S is speed. It's really important you don't confuse the two. Another equation you should know is one for acceleration. So this is where acceleration is equal to the change in velocity divided by t. That's what that triangle means, that delta, and also the Suvat equation that you could link to this. So there is one that is velocity squared minus initial velocity squared is equal to 2 times the acceleration times the displacement. You are given that equation along with the acceleration equation, but just knowing what those symbols mean is really important to unlock and actually access the course. So definitely practice those types of equations and you know how to rearrange them. If you need any help, do let me know in the comments section below. You also need to know two different graphs. So there's one that's the speed, distance, time graph you may have seen before. So you've got time and distance on the axes there. So let's have a look at how this information can be graphically represented on a distance time graph. A distance time graph essentially shows you how much distance is made in a given time. And therefore the gradient tells you how fast that object's moving. So you can work out the speed from a distance time graph. The steeper the gradient, the faster the object will move. And if we have a curved line on a distance time graph, that tells you the object is actually accelerating. You also need to know another type of graph, the velocity time graph. And essentially, you could be asked to work out the area under the graph, and this will equal the distance that has been moved. Another concept for higher tier students is this idea that objects that move in a continuous circle will actually have a constant speed as they're moving, but they're changing their velocity as the object moves. Remember, velocity is a vector quantity, so it has direction as well. And if an object is moving in a circle, it's constantly moving direction, which means the velocity is changing. However, the speed of that object is going to be constant and remain the same. Last but not least is this idea of forces and braking. Remember that the stopping distance is equal to the thinking plus braking distance. Remember things like road conditions, drugs, caffeine, sleep, all affect reaction time. And large decelerations can actually lead to the brakes overheating. So if you're going at a very fast speed and then you suddenly decelerate and try and slow down, this can actually cause an increased amount of friction, meaning the brakes can overheat, and this is a big problem in terms of safety. So the next topic is waves. Remember, waves transfer energy but not matter. There's actually two types of waves that you should know. The first category is called a transverse wave, and this is where vibrations or oscillations are at right angles to the direction of wave travel. However, in longitudinal waves, these are waves that have vibrations which are parallel to the direction of wave travel. As you can see, they do have some similarities. Let's go through some of the key labels. So a peak or a crest is the top of that wave. A wavelength is from one peak to one peak, or one trough to one trough, or from one specific area to the next on that wave. The trough is the bottom part of that wave, and the amplitude is the height of that wave from the midpoint. In terms of longitudinal waves, there are a couple of different labels you should know. So compressions are the amount high regions of pressure due to the number of particles being close together. We also have rarefaction, which is when those particles are spread out and they're no longer compressed. This is why longitudinal waves are essentially sound waves, so ultrasound, the sound that we hear as well, because particles help transfer that energy. A couple of other ideas: frequency and time period. Remember, frequency is the number of waves per second, and the time period is how quickly those waves travel in a given amount of time. There are two equations for this. So time period is equal to 1 over the frequency. Remember, frequency is measured in hertz and time period is measured in seconds. We also have velocity, which is equal to the frequency times the wavelength, which is given the symbol lambda. Remember, velocity is measured in meters per second and the wavelength is measured in meters. Now, there are a couple of required practicals that you should know. The first is looking at waves in a liquid, and another is looking at waves in a solid. So the ripple tank experiment and the stationary or standing waves experiment are both really pinnacle and important that you know how to do them. I have got videos on them, so I'll link those for you. But essentially, you're looking at how waves are transferred in different mediums. And this links nicely to this idea of reflection and refraction. So the law of reflection tells us that the angle of incidence is equal to the angle of reflection. And you can see that on that diagram there. So the dotted line shows us the normal line. And essentially, this is just a 90-degree angled line from the object. And as you can see, the angle of incidence, that red line, is going to be the same exact angle as the angle of reflection that comes straight out, that orange line. And you should be able to draw ray diagrams, especially if you're a higher tier student. You should be able to draw them for refraction as well. So refraction essentially is when light waves essentially travel through a different medium, and the density of that medium actually causes that particular light wave to bend. And as you can see in the diagram here, you can see that the line has actually started to bend towards the normal line, and then it continues on its path as it leaves the medium. So you should be able to draw that, and that's why we see things like straws in water that are kind of bent. The Leslie cube practical essentially helps us to see how infrared radiation is either absorbed or reflected. So a Leslie cube is a metal cube that has different surfaces, and essentially you can fill it with boiling water, and you'll be able to see and measure that infrared radiation that's being emitted from the surface. Now, the different surfaces depend on whether they're matte black, shiny black, there's a matte white, and there's also a shiny metal surface. So what you want to do is place the Leslie cube on a heat resistant mat for safety, and you fill it with, like I said, boiling water and place a lid on top. You want to leave this for a minute or so, and this is to enable the surfaces to heat up to the temperature of the water. Then what you're going to do is use an infrared detector to measure the intensity of infrared radiation emitted from the surface or the temperature of the surface, and make sure that the detector is the same distance from each surface as you make your readings. I would recommend you do multiple repeats of this and calculate a mean average. And then what you're going to do is to work out the difference in each of these. You want to plot the data as a bar chart, and that will give you some results which you can compare. So in your results, you'll be able to see the different surfaces for the best emitter and the worst emitter of infrared radiation. And usually you're going to see that the matte black surface will actually have the highest infrared intensity, whereas the shiny metallic surface will have less of an intensity. So, another type of wave that is found in the category of transverse waves is the electromagnetic spectrum wave. So, you need to know that all of these waves from radio, micro, infrared, visible light, UV, X ray, and gamma, these are all part of what we call the electromagnetic spectrum. Now, these waves, like I say, are transverse, so they do transfer those vibrations at right angles to the direction of travel. And they also are able to transfer energy from the source of the wave to an absorber. So let's say, for example, we take the idea of microwaves. We use these in satellites, but we also use them to cook our food. Now, the source of that microwave is actually going into that energy is transferred into the water molecules inside the food, and it causes them to become excitable, if you will. So, the internal energy, that potential and kinetic energy inside those water particles of food, actually start to gain energy and they start to vibrate more. This is what actually causes that increase in temperature. Remember, kinetic energy increases that thermal energy, and that is why the food starts to cook and heat up. Now, the same can be said for other examples of electromagnetic spectrum waves. So UV waves, for example, we find this in the sun. They are transferred to our body. They do have risks associated. If we are exposed to too much UV, it can be very ionizing. The same could be said for X-rays and gamma waves. But essentially, these are all waves that transfer energy. The only one we can see is visible light. So don't forget that one is one we can actually physically observe. The rest of them, we can't. We can detect them with devices, but we can't see them. Now, you do need to know what they are used for. So radio waves, as the name would suggest, are used for radios and television. Microwaves, I've said, are used for cooking food and for satellite communication. The infrared radiation is used for electrical heaters, cooking food, and also infrared cameras. Some actual animals and reptiles and frogs can actually see infrared, so that's pretty cool. Visible light, obviously, this is used by ourselves. We can see this, but also for fiber optic communications. And UV can be used for energy efficient lamps and sun tanning, although this is, of course, dangerous and there are risks associated. X ray and gamma rays are used for medical imaging and treatments as well. Now, there is another medical device called ultrasound, but this is not a transverse wave. Ultrasound is used for essentially imaging soft tissues, so it's used during pregnancy and things like this. However, that is an example of a longitudinal wave. So we have the last topic, magnetism and electromagnetism. Now we have an example of a permanent magnet, something that is consistently producing magnetic fields, and this is the bar magnet. Now this has two ends called poles, the north pole and the south pole of that magnet, and those poles are where the concentration of the magnetic force is the strongest. Although those field lines do not cross, this is where that force of magnetism is the strongest at those poles. So you need to know that the magnetic field actually goes from the north to the south pole. So whenever you're drawing your magnetic field lines, they don't cross, but they do have an arrow from north to south. You also need to know that this is an example of a non-contact force that is being produced here. You also should know that there are two types of forces in this case. There's this attractive force between the north and south pole. But if you flip two magnets around and you have the south and south pole facing or the north and north side facing, this will actually produce a repulsion force. They won't want to be forced together. You never want to say they stick together or they are stuck together because that is not accurate. You want to say they repel or they attract. An induced magnet is an object that's made of magnetic material. So it's either made of iron, steel, cobalt, or nickel. Remember, steel is a ferrous metal, meaning it contains iron. So it's actually an alloy. It's a mixture of something. But an induced magnet is either made out of any of those materials. And as soon as it's placed into a magnetic field, it starts to become magnetic itself. Now, it can only attract magnetic objects. It cannot repel. And that's a really good indicator to tell if it's induced magnet or permanent. You could also remove it from the magnetic field as well, and that way it will actually remove its magnetic ability. So that's a good way to test to see if this works. Lots of times in the exam they'll give you diagrams to kind of help you explain the difference, so it's worth knowing those differences and being able to identify induced versus permanent magnet. Now, you do need to know how to plot magnetic field lines around a bar magnet, so you would need to use a compass for this and a pencil and also a ruler as well. Remember, those field lines should never converge, they should never cross over. And you should also remember that you need to draw arrows from north to south and follow that compass around the bar magnet to show that direction as well. You also need to know that the Earth has a magnetic field and a compass itself has a bar magnet, and this is why this works in this practical. The Earth has an iron core, which is why we know it has a magnetic ability, or it has those poles, the north and south. Now, another thing you should know is this idea of the motor effect. So when a current flows through a conducting wire, a magnetic field is produced around the wire. Now, the strength of the magnetic field will depend on the current through the wire and the distance from the wire. So magnetic fields around a solenoid will be produced, as you can see in this diagram. And a solenoid is essentially going to act in this case like a bar magnet. You can see the diagram is the same. A solenoid, by the way, is just a wire that has been wrapped around itself into a coiled shape, and we can strengthen the solenoid's magnetic field by actually adding an iron core, and this is therefore now considered an electromagnet because it has that iron core. So we need to also be able to, as a higher TS student, know how we can use this idea, Fleming's left-hand rule and the motor effect. So Fleming's left-hand rule basically shows us, by using our left hand, the direction of the force and therefore the movement of an object, the magnetic field direction and the current in a wire, looking at using an electromagnet or a solenoid. So you've got some examples here I've drawn for you. We've got two bar magnets from north to south. You can see that magnetic field is pointing. We give magnetic field or magnetic flux density the symbol B, and this is measured in Teslas. And if we use our left hand, if you point your first finger, the magnetic field finger, in the direction of the arrows, you'll be able to see that the current actually points outwards as well, because that wire is showing current outwards. You'll then be able to work out which direction the movement or the force is acting. And in this case, if you were to do this, you'll see the force acts downwards. Now, what happens if we switch the current around, or we switch the magnetic field around? Well, tell me in the comments, what do you think would happen then? Remember the equation, force is equal to magnetic flux density times the current times the length. Magnetic flux density B is measured in Teslas. Current is the symbol I, but it's measured in amps. And length is measured in meters, where force is measured in newtons. Be careful of current with the symbol I. It's the units A that you're going to need in this case. A really big common mistake that is done with students. Okay, the next one is the motor effect. So although we can use this idea of Fleming's left-hand rule, you also need to know that the motor effect actually helps us to turn objects. What is the motor effect? When a conductor carrying a current is placed in a magnetic field, the magnet producing the field and the conductor exert a force on each other. And we can use the motor effect in electric motors to rotate objects. So a motor is something that will continuously rotate. And higher tier students need to know that this is because if you use a split ring commutator, it actually will change the current's direction and allow for rotation. So every 180 degrees, the current will flip direction and go in the opposite way. And that means the force is actually changing direction continuously, which means you get that rotation. And that's it from me today. I've been a GCSE science teacher and you have been curious. I hope you found that video helpful. If you did, let me know by giving the video a thumbs up. Share it with someone else so they don't miss out on key revision. And if you have any tips yourself you would like to share in the comment section, feel free to do so. If you've learned something from this video, let me know. It's always great to hear from you. And of course, if you would like to subscribe, please do by clicking the subscription button. It's absolutely free, and the bell to stay notified. Thank you so much for watching. Thank you for your support, and I will catch you in the next one. Good luck for your exams.